All right. So today we are talking about section 6.3, and we're talking about solutions about singular points. And what we might want to recall is that from 6.2, we actually looked at solutions about ordinary points, right? And in 6.2, when we talked about ordinary points, we sort of described this class of points. And then we said, well, if it doesn't fulfill the ordinary characteristics, then it's going to be a singular point. Okay. And so what we're going to take a look at right now is just these two equations right here, right? They look so very similar. The one on the left says y double prime plus xy equals 0. And the one on the right is the coefficients are switched. X, y double prime plus y equals 0. Okay. And so when we take a look at this first differential equation, we might notice that a sub 2 of x is 1, right? And so what we learned about 2 days ago was if a sub 2 of x is not 0, and there's no other sort of discontinuities in the other coefficients, then we can classify that sort of situation as having an ordinary point. Okay. Now, we did in our problems specify for the most part that x equals 0 was going to be sort of our center point, our ordinary point. That doesn't always have to be the case. It was genuinely to make the computations as easy as possible in what we saw was a pretty long kind of problem. Okay. And we sort of talked about this, but we didn't touch upon it a whole lot, where sometimes if we have that coefficient, all right, and in this case, our a sub 2 of x is x. But if we were to take this differential equation and rewrite it in what we call standard form, where we divide away that leading coefficient, we would get y double prime plus 1 over x times y equals 0. And so once we've divided that away, even though this doesn't equal 0, like that leading coefficient doesn't equal 0, we end up with a coefficient later on in the differential equation that does have a discontinuity. Okay, and so because this has a discontinuity at x equals 0, we're going to say that x equals 0 is a singular. Okay. So that idea of is it continuous, is it not, really helps us play into is it ordinary or is it not? Okay. And so today, what we're going to talk about is classifying singular points. That's where we're going to start our story. We're going to classify them, and then we're going to describe a process in which we can predict the number as well as the type of solution. But we're not actually going to find those solutions, okay? If you want to, out of the nerdiness of your own heart and brain, you can read through section 6.3 on your own. There are more examples in there where they actually solve the different series. I just didn't think it was necessarily quite as important as some of the other stuff we have coming later in this course. Okay. All right, so we're going to begin our story with singular points in the same way that we did for ordinary points. So we're going to recall that we could have a second order linear differential equation, and it's homogeneous. And if we divide away that a sub 2 of x, we'll end up with this form that we've seen quite frequently, right? Y double prime plus p of x, y prime plus q of x, y equals 0. Okay. So a few things about this. A point that is not ordinary is singular. Okay, a point that is not ordinary is singular. And we can classify singular points in actually two different flavors, okay, or two different types. So what flavors do they come in? Well, we can say that there are something called regular singular points. And then we can say that there's something called irregular singular points. This definition looks much more complicated than it is. The basic gist of what we're going to do today is a whole bunch of factoring, a whole bunch of setting things equal to 0 and solving. Okay, so if we are good with the factoring, today should actually be a pretty nice way to end week 6. So let's look at the definition though, and maybe we'll come back to it after we've tried a few problems to see if that makes sense. All right. So a singular point is regular if the following two things are true. Okay, so I want to be clear here that both of these characteristics need to be true. And the first one is that we have this lowercase p and this lowercase q, okay? And if that equals x minus x sub 0, so whatever that center point is, times p of x, if that is analytic at that point, that is one clue to say that that point is going to be a singular point, a regular singular point. But it also must be true that that second coefficient actually is equal to, if we have that second coefficient times x minus x naught squared. Okay, so that's definitely something different here. This one has a squared. The first one does not. If that is analytic at x equals x sub naught, then we are good. Okay, we will say that is regular. Otherwise, the point is going to be an irregular singular point. Okay. Now, again, I don't really love these definitions, but I wanted to make sure that they're out there so we can start to think about like making sense of some more grown-up kind of math stuff. Okay. And so let's go ahead and take a look at this first example, and then we'll kind of revisit the definition, see if we can modify that to make a little bit more sense for ourselves. All right, so we're going to begin with this equation. All right, so we have this second order differential equation. It has non-constant coefficients. And in particular, you'll notice we're working with a lot of polynomials. Okay, these don't have to be polynomials, but in polynomial land, it makes things a little bit easier in terms of what we're trying to accomplish. All right. But our first thing that we should do here is not FOIL everything out. Okay, do not multiply everything out. The first thing we should do, however, is just like we did up here, how we had this differential equation and we divided by that leading coefficient and we got the one in standard form. The first thing we're going to do is we're going to take that equation that we have and we're going to turn it into standard form. So let's do that. And we are going to be keeping most things unsimplified, though it may be valuable to continue factoring if indeed that is helpful. Okay, so the first thing I'm going to do is I'm going to divide the entire equation by x squared minus 4 squared. And so we're going to get y double prime plus 3x minus 2 over x squared minus 4 squared y prime plus 5 over x squared minus 4 squared y equals 0. Okay. So all we did was divide things away. Now, noticing that I have some factors here that are already factored, like for example, 3 times x minus 2 is already good to go. But it might be valuable for us to take that x squared minus 4 on the bottom and factor that. Okay. And so when we do that, anybody watching the Olympics? No. Trying to. I know it's hard with the time change. But I used to play rugby, and the women's rugby was on last night, and so I was up at like all hours of the evening. I know they don't make it easy. You have to have all these logins or like friends that have logins to watch anything. But I was definitely up too late to be 100% functional this morning.
How
Anyway,
they do?
what's that? Oh,
How
how
they
did
do?
they do? The US won both of their games, which is great. And actually, one of my roommates is coaching the Japanese women's team, and so I was up watching the Japanese game as well. They did a little bit less great, but that's okay. They're working on it. So, but I think day 2 is tonight. So I'm really glad that we don't have class tomorrow. That's where I'm going with that. All right, so let's factor though. We've got 3x minus 2 all over. So I know that x squared minus 4 is x plus 2 times x minus 2. But since I'm squaring them, I'm going to sort of clump them as x plus 2 squared and then x minus 2 squared. Okay, so like there's one x plus 2 and x minus 2 from the first x squared minus 4, and then there's a second one from the fact that we're squaring it. And then I'm not going to forget the y prime plus 5 over, we'll do the same thing here, x plus 2 squared, x minus 2 squared, y equals 0. Okay. And so what we're going to take a look at here is we're going to start by taking a look at our new capital P of x and capital Q of x. Okay. So if we were to sort of color code things, we might notice that this capital P of x is the one in front of the y prime. So that's going to be this whole blob right here. And then we also have a capital Q of x, and that's going to correspond to this whole blob right here. All right, so what are we going to do from here? Well, the first thing we're going to do is we're going to go ahead and take this original coefficient, and we're going to solve for 0. Okay, so let me write that out. So we have our standard form. We're going to go ahead and find where a sub 2 of x equals 0. And so we end up with x squared minus 4 squared equals 0. We know from our previous factoring that that's really the same as x squared minus 4 equals 0. Or we could say this is x equals plus or minus 2. Okay. So we sort of have these two values here, and now we need to work with these two values to help us determine the rest of the question, okay? And so what we're gonna do is we're gonna take this, these two values, and we're gonna pretend that they're two different factors, okay? So we're gonna write one as like an x minus 2 factor. We're gonna write the other one as an x plus 2 factor, all right? And here's what we're gonna do with them. These 2 points, x equals positive 2 and x equals negative 2, those are points that we need to consider as if we multiply them by our capital P of x, or if we square them and multiply them by our capital Q of x, are we going to get something that is analytic or not? Okay. And so we might say that our third step here is that we're going to go ahead and what's the best way to organize this? Okay. for x equals 2. All right, so let's start with that one. For x equals 2, we know that the corresponding factor for that would be x minus 2. And so what we're going to do with that is we're going to take x minus 2. We're going to multiply it by our green blob p of x, all right, to make little p of x. And then we're going to take a look at what that says, okay? So we're going to take x minus 2, so little p of x will equal x minus 2 times 3x minus 2 over x plus 2 squared times x minus 2 squared. Okay, so I've taken my capital P of x and I've multiplied it by that factor. And we'll notice that quite a few things actually reduce, right? And in particular, we have an x minus 2 and an x minus 2, and that's going to reduce with the x minus 2 squared. Okay. Now, what do we have left? We have 3 over x plus 2 squared. Okay. I'd like you to do the same thing for the q of x, except this time we notice that for the q of x, we need to have that x minus 2 squared. Okay. So you're going to set things up the same way. And you're going to multiply, since we're looking for the q of x, you're actually going to multiply them by the purple term. Right, so take a moment and do some reducing. Let's see what we end up with. All right, and I think we'll notice that this x minus 2 squared and this x minus 2 squared reduce. And we're going to end up with 5x plus 2 squared. Let's go ahead and just practice that procedure again. And I'm going to have you try that for x equals negative 2. Okay, so for x equals negative 2, write down what you think the corresponding factor is, and go ahead and find that little p of x and that little q of x. Okay, I'm going to just check a message real quick because I think my Calc 1 students, their exam just closed, and I think some of them are panicking a little bit. Hold on. Sorry. It's their last exam today, so I think I told them I would not be accepting late exams, so I think they're panicking a little bit, but okay. So for x equals -2, the factor that goes with that is x plus 2. And so if we set up our same idea of little p of x and little q of x, this time we're not going to multiply the green and the purple by x minus 2, but we're going to multiply by x plus 2. And don't forget, for the little q of x, we're going to need to say that equals x plus 2 squared times that purple blob. Okay. So now let's go ahead and reduce. And then now that we've had all 4 of them, we can kind of compare and contrast and see what's happening. Okay. So one of these is going to reduce with one of these, and one of these is going to reduce with one of those. Looks like both the x plus 2's reduce here. And so we're going to end up with 3 over x plus 2 times x minus 1. And over here, we're going to end up with 5 over x minus 2 squared. Okay. All right, so what in the world does all of this mean, right? We're doing this procedure, but it's really important that we know what all of this means, right? And so when we want to think about what's happening, what we're looking to do is say, really, are these points regular or are they irregular? Okay. And so the difference between the irregular and the regular is really thinking about how many times a certain factor is going to show up in that denominator. Okay. So after we've multiplied everything through, what still shows up and what does not. Okay. And so I actually want to start with the one that is the p of x over here. Okay, this one. And the reason why I want to start with that one is because even though I followed the same process for everything here, this answer stands out a little bit more than the others. And the reason it stands out more than the others is thinking about, like, if we were to think about compare and contrast, like what happened when we plugged in something versus what came out, we might notice that here we multiplied by x plus 2, but at the output, we still had an x plus 2 in the denominator, right? So the thing that we multiplied by still showed up. What does that mean? That means that if I plug in -2 into the little p of x here, it's still going to give me something that is undefined, right? Because if I plug in -2 for x, this first factor will go to 0. And then I have 3 over 0, which we all know is undefined. Okay. But let's see if that's the case with all the other ones, right? So for x equals 2, if I plug 2 into what I get for the output, do I end up with anything that could possibly be undefined? And I think that our answer is no, right? Because if I plug in 2, I'm going to get 3 over 4 squared, and that's all good. That's defined, right? What happens if I plug 2 into this one? Well, I'll get 5 over 4 squared. That's defined, right? If I jump down to this last one, 5 over, this time I'm plugging in -2, so 5 over -4 squared, that's still a real number. That's good to go. Okay, it's defined. But the only one that kind of stands out at the end of this process is this one, because I still end up with an undefined value at x equals -2, okay? And so the way we classify these, okay, we're gonna say that x equals 2 is a regular singular point, whereas x equals -2 is an irregular singular. Okay. So we have a regular singular point and we have an irregular singular point. Okay. So we could have both in terms of the type of problem. Okay. But the gist of all of this is that if we go back and look at this in the bigger picture story, right? We're going to take our differential equation, we're going to turn it into our standard form. But we're also going to consider maybe like step 1 and step 2 are sort of like at the same time. We're considering what possible values might make that leading coefficient equal to 0. And after we identify those, then we sort of, for each one, we go ahead and plug it into this equation here and determine whether it is that function is analytic around that point or not. And it is possible to have a mix of regular and irregular singular points in the same equation. Okay. And so let's go ahead and take a look at, didn't do my spacing very well. Let's take a look at another example. Okay, so part of this is I want us to practice that procedure and practice that factoring. I noticed that some of us still very much are dependent on the quadratic formula. And I would say at some point, those training wheels have to come off. Okay, it will take you longer to use a quadratic formula than it will to factor if you put in the time. Okay. And so I'll give you a moment to take a look at example 2. Okay, you're going to go ahead and turn that into standard form. And then you're also going to go ahead and find where a sub 2 of x equals 0. And you can sort of attack these in whatever order you see fit. And I'm just going to check these messages to see who's panicking about things. Okay, give me 1 second. think I forget how stressful Calc 1 can be sometimes. All right, so let's turn this into standard form here. Okay, so we're going to go ahead and divide everything by this x cubed plus 4x on all of the terms. So we're wanting to make sure we divide this first one, but I don't know why sometimes that last one, we just kind of forget to divide by that as well. So just make sure if you're dividing this coefficient everywhere, that is here, 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 and technically the 0 side, right? But that's the nice thing about it being homogeneous. You don't really need to worry about that part very much. And so if we divide this away, we're going to get y double prime minus 2x over, and I'm going to go ahead and factor this x cubed plus 4x while I'm here. And so I get x times x squared plus 4 in the denominator. There's a y prime here plus 6 over x squared plus 4, y equals 0. And then we want to see what are our possible singular points, right? In fact, what makes that leading coefficient equal to 0? And so we'll have x cubed plus 4x, which we know factors into x times x squared plus 4. We're going to say what values of x make that equal to 0. Okay. And so what are our thoughts here? What values make this equal to 0? Okay, I buy that. I would say x equals 0 is a value. Anything else? Good, good. Okay. And I'm really glad that we made a point to say this is a plus or minus 2i. I know that like once upon a time, this is probably so long ago for you, but when you were in like probably early high school, you're like x squared plus 4, you're like, there's no factors. And then someone was like, but there's imaginary numbers. And you were like, oh, okay, right? It's like this whole new realm. But it is important to sort of think about those and how they might come into play. Okay. But as far as what we are looking at, we're really looking at finding like, what are the real situations? So I want us to be aware that we have the plus or minus 2i, but how that plays out might look a little bit different. Okay. So let's start by finding, how did I phrase this up here? 4. Okay. So for x equals 0, okay, let's go ahead and find our p of x and our q of x. And when I say that, I mean little p of x and little q of x. And we're going to find little q of x. Okay. And when we go ahead and reduce, based on what we have here, do we think that x equals 0 is a regular singular point or an irregular singular point?
Regular here, right?
Yeah. So we have, if we look at the denominator, right? I still have an x squared plus 4, but if I plug in 0, that's not going to give me anything undefined, right? I'm not going to get 0 in the denominator. I'm not going to get 0 in the denominator here. I'm not going to get 0 in the denominator here. And so we have a regular singular. Now, again, we're looking for these real values, okay? So we know that we have this 2i and a negative 2i, but the only real one that's coming up is x equals 0, okay? So that is the only one that we need to check. But when we take a look at example 3, we're gonna have a lot more possible singular points, okay? So we'll have, I think in number 3, we're gonna have 4 different points that we're gonna wanna check, okay? So we're gonna get a chance to do the standard form, find those possible singular points, and then this third step, we're gonna do for 4 different points, okay? And so let's go ahead and take a look at that. All right, we'll go ahead and turn that into standard form. Or if you wish and it makes more sense to you, you're going to find that singular point values or where a sub 2 of x equals 0. Okay, so take a moment to do that. It's actually probably very refreshing to deal with only factoring, right? You are at the point in your career where it's only factoring. It's not then plugging things into a bazillion series and trying to make it into a single series, right? Right. I have not written the standard form yet, but I have found the singular point values here, the values that make that leading coefficient equal to 0. And so if you're already at that step and your values check out with mine, you can go ahead and start testing each one to see, is it regular or irregular? Okay. And I'm wondering if, for the sake of trying to be somewhat collaborative, which I know is hard in this online format, if everyone could choose their favorite singular point out of the 4 listed values, right? So I know there's not that many of us, so maybe not everyone picks 0, right? Maybe someone could pick -5, maybe someone could pick +5, maybe someone else could pick 2, and we could all just kind of go through that process. Yep, thank you. If you want to step up and claim a number, that is absolutely fine, all right? And as long as every number is represented at least one time, I think we'll be good to go. And we'll just sort of share out what our results are for that before we move on to the last part of today, which is what in the world do these singular points actually tell us as we're looking at a different kind of series solution. Okay. And if you're scared you did it wrong and you don't want to put it out in the whole chat, you can just send me a direct message. This is the beauty of the online learning format, right? Not that many beautiful things, but it is a nice thing. You can sort of whisper your answer to me and it will be okay if it's not right. All right, looks like we've got some stuff coming through. Good. Yep, I got regular for x equals 2 as well. Yeah, I think x equals 5 is regular as well. This one is regular. You tried positive 5. That one I agree is regular. Anybody find out anything about x equals -5 or x equals 0?
I got regular for x equals -5.
Yes, yes. Good, good. All right. I hope someone did 0. I know I said I don't want everyone to do 0, but then I hope that didn't result in no one doing 0.
I think for x equals 0, you're just going to get irregular because of that x cubed on the bottom, right?
Exactly, exactly. Right. So the denominator has that cubed, but it only shows up twice in that little q of x. So there's still going to be one x in the bottom. And so that x equals 0 is indeed an irregular point. Okay. You folks are so kind. All right. So a good sort of practice in factoring and dividing and things like that. Okay, so if you're feeling a little bit rusty with that, no worries, you can still practice that a bit and get back up to speed with the factoring. If you've still, up until this point in your math career, never learned factoring, it doesn't go away. I genuinely don't think I've ever taken a math class where I don't factor. Okay, so it's not too late is what I'm saying. It's not too late. Okay. So the second part of our story, again, is more around like, well, why does this matter? Okay, and we're not going to get into the procedure, but we are going to get into sort of why this matters, whether something is a regular singular point or an irregular singular point. Okay. And so it turns out that there is something called the method of Frobenius. I think Frobenius did quite a few things in differential equations. Also, there's something called a Frobenius number that deals with sort of how do I best describe it? Well, it doesn't matter. Anyway, Frobenius did a lot of things. Okay, so Frobenius, he came up with this method to find a series solution specifically around regular singular points. Okay, so if you're asking yourself, like, why do I need to classify? Like, classifying is fine. I can, divide, I can factor, that's great. But like, why is it important? It's important because it would be the first step in saying, okay, I found this regular singular point. And once I find this regular singular point, it turns out that Frobenius said, if you have this regular singular point, then there will be, and these are maybe some of the least favorite words in mathematics, at least one, all right, at least one solution of the following form. And that is y of x is going to equal the sum from n equals 0 to infinity of some constant x minus that regular singular point to the power of n plus r. Okay, so two things about this should tell you why we're not going to be solving these. Okay, the first thing is there's at least one of these. There could be two. Okay, the other thing is this power situation up here means that we're shifting by different values right now. Okay, now r is a constant. All right, R is a constant, and that it's something that we'll actually be able to figure out using what we call this indicial equation. Okay, so it is something that we can find, but the more challenging part is now we have this idea of something that's not quite a nice power series. Okay, so as gross as 6.2 was, that was almost like a better case scenario than what we would embark on if we tried to use the method of Frobenius. All right. And so it turns out that we can use indicial equations to predict, right? So that's the key word. This is what we're going to work on. We're going to predict how many solutions and the type of series solutions, like what does it look like? Okay. And I am primarily concerned with the ability to sort of predict the number, and then the type of series. I wrote it down here in the notes. I would not expect you to memorize this. I don't think that any instructor would expect you to memorize this per se. It is more just about knowing that there's different forms to those series solutions. Okay. I do want to make this part really clear. We will not be solving problems that involve the method of Frobenius. Okay, it's a fairly complicated task, and it's just not something that is perhaps the most important to walk away from an intro-level differential equations class. Okay, so we will not be solving these problems. Do not read 6.3 like that second half in 6.3 and start to panic and think that you missed something in lecture. You did not. All right, we're not going to be doing the solving part. But here we have this indicial equation. Okay. So R minus R sub R times R minus 1 plus A sub naught. I'm missing a letter. There should be an R right here. Sorry. A sub naught R plus B sub 0. Okay. And if I were to write that out, because I don't want us to think this is an exponent, R times R minus 1 plus A sub R plus B sub 0 equals 0. Okay. Now the chart that follows here, your three cases, all right? So you plug your values in there, and what you're going to be plugging in is your A sub 0 and your B sub 0. You plug in A sub 0, B sub 0, and you go ahead and factor. And you end up with an R1 and an R2 that are different from each other. Okay. So the first two cases are going to look at R1 and R2 being different from each other, whereas the last case, R1 and R2 are equal to each other. All right. So that might be a good question to ask yourself first. Are my two roots equal to each other, or are they different from each other? Because if they're different, you're going to use case 1 or 2, but if they're equal, you're going to use case 3. But for case number 1 and 2, there's actually an additional layer that we need to consider. If I take R1 minus R2 and it is not a positive integer, then we're going to have the following forms of solution. However, if we take the difference here and it is a positive integer, we're going to have these two types of solution. So being able to identify what type of roots you have and whether they are different or equal is definitely really important. Okay. I did notice on the exam that some folks factored incorrectly. And so if you factor incorrectly, it might lead you to write down the wrong form of the equation. Okay. Or if there is a situation people factored correctly, but then they chose the wrong form of the solution to plug it into. I know we've talked about so many different forms, like, oh, if we see this, then it's going to look like this. And if we see this, then it's going to look like that. But that is actually a very important skill to have in differential equations, that you really want to be thinking of matching your result. A lot of these come from the different roots of these equations we've been solving, right? The roots of those equations and matching it to the correct form of the solution. All right, so I would just encourage you to double check that for like an exam or a homework or something like that. Okay. So these three solutions, we'll look at them a little bit more deeply when we take a look at our questions in just a little bit. But one question you might be asking yourself is like, okay, well then how do I find a sub 0 and b sub 0? And that's a super valid question. We should be asking ourselves that question, right? So to find a sub 0 and b sub 0, we're going to use something that should seem pretty familiar to what we used above to determine whether a point was regular or irregular. Okay. So if we have p of x, little p of x equals x p of x, it turns out that a sub 0 is the first term once we distribute. Okay, it's going to be the first term once we distribute. It turns out that this little q of x, when I do x squared times big Q of x, b sub 0 is the first term here. Okay. All right. So knowing that, let's go ahead and take a look at what we have for our examples. All right. So we have this example for, we have 2x y double prime plus 1 plus x, that quantity, times y prime plus y equals 0. And so the first thing we should be thinking is, let's go ahead and turn this into standard form, right? We want to know what our capital P of x is and what our capital Q of x is, right? So let's go ahead and turn that into standard form. And when we do that, we'll get y double prime plus, 1 plus x over 2x y prime plus 1 over 2x y equals 0. The next thing we're going to do is we're going to find our P of x and little q of x, right? So little p of x and little q of x. And so little p of x is going to be x times my capital P of x. So 1 plus x over 2x. And if I go ahead and simplify that, I'll end up with these x's reducing, and I'll get 1 plus x over 2. Okay. 1 plus x over 2. If I go ahead and find my q of x, I'm going to have x squared times this clump over here, 1 over 2x. And this gives me x over 2. So, a little bit formulaic here. We found our P of x and our Q of x. Now, in order to find our A sub 0 and our B sub 0, all right, earlier I wrote A sub 0 is the first term and B sub 0 is the first term. And here's what we mean by that. The first term means we're going to take this, and all we're going to do is we're going to plug in 0. Okay, we're going to plug in 0. So third step, we're going to find our A sub 0 and our B sub 0. And all that means is we're going to take each one of these, we're going to plug in 0, and we're going to see what we get. So a sub 0 is going to be 1 plus 0 over 2, which is 1/2. And b sub 0 is going to be 0 over 2, which is 0. Okay. All we're doing is plugging in 0 to go from finding our p of x and q of x to finding our a sub naught and our b sub naught. And it would be entirely accurate to write a sub 0 as like little p of 0 and b sub 0 as like little q of 0. That would be okay as well. Okay. I just wouldn't plug in the numbers until after you've simplified. I think that would be a really important step, right?
Professor, just really quick for p of x and q of x in black, we got the x and the x squared from where again exactly? Just so I'm clear.
Right up here.
Okay. Okay. Thank you.
You're welcome. I know this is one of the things that I sort of dislike about differential equations. You're like, oh, it's just this formula, right? And we don't always spend as much time unpacking like where those formulas come from, but I think that comes up later if you take like a sort of like graduate level math class. All right. So I didn't reduce this here, but I could have done that as well. All right. And then our last step here, so that we can figure out what kinds of solutions we might have and how many of them there are, we are going to set up and solve the initial equation. Right. And so that equation, just as a reminder from above, because I missed that r in the in my typing of it, r times r minus 1 plus a sub 0 r plus b sub 0. And we want to say, when does that equal 0, right? And so now we're just going to plug in the a sub 0 and the b sub 0 we found, and then go ahead and go from there. So we have r times r minus 1 plus 1/2 r plus 0 equals 0. We get r squared minus r plus 1/2 r equals 0. This gives me r squared minus 1/2 r equals 0. Please do not use the quadratic formula for that, okay? We need to know how to factor things like this. This should be in our factoring wheelhouse for sure, for sure. r minus 1/2 equals 0. And so we get 2 roots, and I'm going to write them over to the left just because I ran out of room over there. We have r equals 0 or r equals 1/2. Okay. And so one question that you might have been asking yourself, which is 100% valid, is in looking at the chart that we had above. Okay, so let's keep these pink numbers in mind. We have r equals 0, we have r equals 1/2. But you'll notice I didn't write like an r1 and an r2 yet. So let's go back up and see. So the different cases. I know that 0 is different from 1/2, right? So I automatically know it's not going to be case 3. But I have to decide, is it case 1 or is it case 2? Okay, because both cases talk about distinct roots. We have to read this part very carefully. Okay, it's not enough to say, oh, is it positive or negative? Right? So if you're reading this really quickly, you might read, oh, it's just one is positive, one's not positive. But it's even more specific than that. In fact, that difference needs to be an integer. Right? In order for case 2 to happen, you need 2 different roots, and the difference between them is an integer. And so if we look at what we have here, 0 and 1/2, I think we can eliminate case 2 because we're not going to get an integer out of a difference of 0 and 1/2. Okay. So what that means is our solutions will look something like this. All right, they will look something like this. All we need to write here, tell me this is case 1. That's it. Okay. I definitely don't need you to solve anything. I don't need you to write out the different forms. You should sort of be familiar with what they look like, but you don't need to write them out. Okay. So when you're working on the homework, you can just say, oh, this is case 1, this is case 2, this is case 3.
Hey, Judy,
Yes.
just did I miss, how do we tell which one's R1 and which one R2? Because doesn't that make a difference for case 2, whether it's positive or not, right? If they were both integers.
Yes. And so I would say this, it's actually less about the positivity and more about the integer value, because you can name them either way. It's still going to end up like you can make an integer and you can make it be a positive integer.
So basically it doesn't matter which one's R1 and R2, but if there is a possibility of results being a positive integer, then you know you're going with case 2.
Yes, that is a great way to summarize that. So if you wanted to write R1 and R2 like that, that would be fine. If you switch the value, that would still be fine, okay? As long as your work lines up with what you have and your reasoning lines up with that, then you're good to go. All right, well, we've got one last question here for us today, okay? And this one, just like the previous one, is going to be a situation where we're trying to say how many types of solutions, or how many solutions and what type are they? Case 1, case 2, or case 3, okay? And so we begin like we started the other ones, which is turn something into standard form. And after we do that, we're going to find our little p of x and our little q of x using the formulas from the previous page. We're going to use those to find our a sub 0, and our b sub 0. And then we're going to plug those into our initial equation so we can determine how these roots work. Okay. So standard form for this one should look like y double prime plus 1 over x y prime plus x squared minus 1/4 over x squared y equals 0. Now, knowing that I'm going to have to multiply some things here, you can reduce this if you want to, or you can leave it like this, okay? And so I'll just show you the sort of alternate form. You may want to write it like this, but you don't have to. I'll leave that up to you. So like x squared divided by x squared is 1, and then 1/4 minus or over x squared is 1 over 4x squared. And so some folks might find this form more helpful, others may not, but I think as you go through the problem, then it'll be a little bit more clear which one you like better. All right, let's find our little p of x and our little q of x. So we've got little p of x is x times 1 over x. And that we can see pretty quickly that that's just going to be 1. And little q of x is going to be x squared times that second coefficient, right? And so maybe if you were unsure whether you should have distributed or not, I think in this case, it actually worked out really nicely that we didn't simplify that term. Okay, so sometimes we look at things that have like a fraction in another fraction, and maybe we get nervous and we're like, oh, should I simplify or not? I would almost hold off on that and just kind of see what you need out of it. All right, that's a big theme in a lot of the higher level math classes, is like keep the structure as much as you can, because a lot of times that'll actually allow you to see the patterns that you want to see. All right, step 3, we're going to find our a sub 0 and our b sub 0. And all we mean for that is now we're going to plug in 0 for x and see what we get. And so a sub 0, when I plug in 0 for into the little p of x, I'm still going to get 1, right? Because it's little p of x is 1. It doesn't matter what number I plug in for x, it's still going to be 1. However, little b sub 0, now when I plug in 0 into this little q of x, I'm just going to end up with a negative 1/4. Okay. All right, let's throw these into our equation. And let's see what we get. R times r minus 1 plus a sub 0 r plus b sub 0 equals 0. All right. Now, I think most of you are probably much more careful with your work than I am, but if you find yourself making mistakes, I would really encourage you to write out the formula so you know that you're plugging things into the right place, okay? But we'll get r times r minus 1 plus r minus 1/4 equals 0. We get r squared minus r plus r, so that r will go away. So I get r squared minus 1/4 equals 0. And that leaves me with r equals plus or minus 1/2. Okay, plus or minus 1/2. And so we can see here that we have two roots, right? One of them is positive 1/2. The other one is negative 1/2. And so my question to you is, can you write these in a way so that r sub 1 minus r sub 2 gives you a positive integer? And if so, which one is your r1? Which one is your r2?
R1 would be positive 1/2 and R2 is negative 1/2.
Yeah, right. If we choose it this way, and I'll include the positive side, r1 is positive 1/2. 1/2 minus negative 1/2 will give us a positive integer. Okay, so in some ways, you might not know right away when you find your roots, which one is which, but if you can make the positive integer, you want your r1 and r2 to work so that you can make that positive integer. This means that we'll be using, or we would be using case 2 if we were trying to find a solution for. Okay. So I'll get that all on one page for you over here. But that, my friends, is 6.3, all right? And really the purpose of 6.3 is just to see where that story would go if we wanted to find series solutions for non-ordinary points. If we wanted to find series solutions for singular points, regular singular points, in fact, we would want to use this method of Frobenius. We would have to be able to identify all of this stuff, okay? But that is where we're going to end our story for chapter 6, okay? So I'm going to stop the recording right now.